Good morning, class. Here's Module 2, covering chapters 3 and 4. Chapter 4, exponential and logarithmic functions. So before starting the exam, please read the following pledge. And this is actually for every exam. I want to remind you, I pledge on my honor that I will neither give nor receive unauthorized assistance during this exam or any other exam for that matter. Unauthorized actions include, but are not limited to, the use of notes, text, graphic calculators, search engines, PowerPoints, AI, that's what's happening nowadays a lot, or any other resources not explicitly allowed. So I hope everybody's clear on that. So having said that, let's start with this example. Find the formula for an exponential function that passes through the points 0, 2000, and 220. F of x is a b to the power of x. So basically, we have two pairs we're going to plug in, and we find two variables missing, a and b. So let's start with 0 and 2000. That means f of 0 or y, which is 2000, equals a b to the power of 0. Okay, so that's the first one. Let's do the second one, 2, 20, in the same manner. That means f of 2 or y is 20 ab squared. So the very first thing we notice, this is 1. So a becomes 2000. So you can replace it right here and say f of x is 2000 b to the power of x. So far, so good. We have one of it. Now we're going to use the second, where it says f of 2, the second equation, f of 2 ab squared is 20. That means that 2000 b squared is 20. Divide both sides by 2000. We get b squared equals 1 over 100. You take a root, and there are two answers, plus minus 1 over 10. It's important to know an exponential function, the base must be positive and can't be 1. Therefore, negative is outside. And it's called an extraneous solution. It's not an acceptable solution. The answer becomes f of x equals 2000 times 1 over 10 to the power of x. Les deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it's compounded monthly? Reminding everyone, the compound interest formula, a of t equals p times 1 plus r over m to the power of n t. What is p? The amount of principal is $10,250. What is r? The rate is 4% or 0.04. What is t? T equals 10 years. So those are given. So we can replace everything here that we have. So it's important to write the given symbolically. So we are going to replace the t with 10, p with 10,250, r with 0.04. And that would be the case in general. Specifically, what happens when it's compounded monthly? First, if it's compounded yearly, for example, n is 1. If it's monthly, n is 12. So all we have to do, replace the n with number 12. Put this into a calculator. First, divide 0.04 by 12, add it to 1, raise it to the power of 120 times 10,250. And you use normally two decimals. In the case of money, we get $15,281.03. Done. Now, same situation. How much will the account have at the end of 10 years? If it's compounded weekly. So that's the difference. So monthly N is 12. Weekly N is 52. So right here, everything is given. Replace the N with 52 for part B. Again, 0.04 divided by 52, add to 1, raise it to the power of 520 times 10,250 gives you the answer. And as expected, is a little bit more, $15,288.85 because it gets compounded more often. How much will the account have at the end of 10 years if it's compounded continuously? And if it does, then the formula becomes A of t equals P e to the power of RT. Okay. So in this case, just replace them accordingly. A of 10. This is $10,250 e to the power of 0.04 times 10. You put that into a calculator and it's a little bit more. It's $15,291.20. In other words, this is the highest amount because it gets compounded continuously. Now, what is the doubling time where A of t equals P e to the power of RT? The concept of doubling with a growth in general, for example, in this case, exponential growth, means the amount of time it takes for the initial amount to double up. So the initial amount is $10,250. However, it's really not important what it is. So you can even keep it as P and how it works because it cancels out. So we are going to write the right side and the left side, A is going to double the initial amount, so 2P. And clearly, we can drop the P from both sides. That's why the doubling time has got nothing to do with the initial value. It doesn't matter what it is. Whatever initial value is, so be it. All right. In order to get to the exponent, you have to take a natural log of both sides. So if we take natural log of the left side is ln2, the right side is simply RT, and therefore T equals ln2 divided by R in general. What is R? 0.04. So ln2 divided by 0.04 is the exact answer, everybody. ln2 divided by 0.04 is the exact answer. An approximation with a bunch of decimals, however many, results in this number. So more than 17 years, 17.32868. As far as the number of decimals, you always write the exact answer and whatever they ask you as far as the number of decimals is concerned. You just follow the instruction. It's extremely important. All right, we are ready to move on. Use the graphs shown to answer the following question. All have the form f of x equals ab to the power of x. Which graph has the largest value for B? Which graph has the smallest value for B? So let's discuss a couple of things. What are exponential functions, class? Exponential functions are in the form of y equals a to the power of x, or sometimes b to the power of x. They write it. It doesn't matter. It's just the base. And if the base a is positive, looks like this, and it's known as exponential growth. If it's between 0 and 1, looks like this, and it's known as exponential decay. And as you can see, the following holds true. For y equals a to the power of x, a, the base must be positive, can't be 1. Why not 1? Because 1 to any power is 1. It becomes a horizontal line. Okay. As you can see, both of them, the domain, it covers the entire x-axis from negative to positive infinity. Range from 0 to infinity, 0 is not included because the x-axis having equation y equals 0 is the horizontal asymptote. Furthermore, you notice both of them have the y-intercept at 0, 1. This is an exponential growth and increasing. This is exponential decay and it's decreasing. For example, this is 2 to the power of x. As we said, if a is larger than 1, looks like that. So any base that is larger than 1 looks similar to that. Okay. This is 2 to the power of minus x. We said a is between 0 and 1. I want to discuss this and show you that h of x is 2 to the power of minus x. It is the same as saying 2 to the power of minus 1 to the power of x, which is 1/2 to the power of x. That's why. So in essence, what we are saying, this is the same as y equals 1/2 to the power of x. So right here, let me erase my work. Right here, instead of 2 to the power minus x, we're going to write 0.5 to the power of x. So this is 2 to the power of x. This is 0.5 to the power of x, or 2 to the power minus x. This is 5 to the power of x. As you can see, both of them look similar. However, when the base is larger on the positive side, in other words, when a is larger than 1, then it's closer to the y-axis. On the other side is the other way around, okay? So why is that? Because it shoots up faster. It's very straightforward. So this is when the function is a to the power of x or b to the power of x, but this one has some number in front of it. When that happens, now class, couple of interesting things happen. First of all, y equals a to the power of a times b to the power of x. Now, the y-intercept was at 0, 1. Now, if you replace the x with 0, replace the x with 0, this becomes 1, this becomes a. So it's located at 0, a now. That's important to understand. So, which graph has the largest value for B? Okay, we're talking about the base. We discussed that. The one that is closest to the y-axis on the right side. So on the right side, we have this one, and this one. This is the closest, so the answer is graph B. What about the smallest one? Same thing, closest to the y-axis, but this side, this time from the left side, okay? So on the left side, you have this one, this one, this one, those three, and this is closest, so graph C. Which graph has the largest value for A? Which graph has the smallest value for A? Well, we said 0a represents the y-intercept. So when x is 0, y-intercept is located at 0a. So we are looking for the largest a or the y-intercept. So here's the one. Look at this one, this one, this one. Obviously, this one has the largest y coordinate. So this point, and that is located on graph C as well. Now, this one is the other way around. Smallest a or y-intercept. So which one has the smallest one? Just come on down, and this one, which is graph F. So to recap what we have, first and foremost, if it's y equals a to the power of x, when a is larger than 1, looks like an exponential growth. Between 0 and 1 looks like exponential decay. The y-intercept is located at 0, 1. Domain is all real numbers, range from 0 to infinity. Horizontal asymptote y equal to 0. If we put a in front, of course, makes the location of a y-intercept from 0 to 1, 0, comma 1 to move to 0, comma 1. Okay. All right, so now we want to use transformation, starting with f of x equals 2 to the power of x, which of course we should know 2 to the power of x looks like that. Okay, it doesn't have to be to scale of the function. And we want to come up with this one, okay? F of x equals 2 to the power minus x, and we're going to state everything, asymptotes, domain, range, you name it. So obviously, as we've mentioned before, this has a y-intercept at 0, 1. And in order to go from 2 to the power of x to 2 to the power of x, you're going to change the x to the power of minus x, assuming x is positive on the right side, minus x on the left side. So it is a reflection with respect to the y-axis. So it looks like that, which means we are not changing the y-intercept. Okay, so this is still at 0, 1, and this is f of x equals 2 to the power minus x. So what we are not changing is that the horizontal asymptote, domain, and range, nothing changes. The thing that changes, this is a decreasing function. So f of x is 2 to the power minus x. We still have the same horizontal asymptote, the x-axis of y equal to 0. Domain is all real numbers. Range is 0 to infinity. This function increasing, this function decreasing. That's the difference between the two. Now, what about this one? G of x is 2 to the power of x plus 1. We are going to look at this one, to the power of x plus 1, the effect of plus 1, shift up, take it up by 1 unit. So we move this up by 1 unit. The very first thing I want you to notice, the location of two things, the y-intercept and the new horizontal asymptote. So the y-intercept location was at 0, 1. Now it has gone up by 1, so must be at 0, 2. Horizontal asymptote y equals 0 is y equals 1. So the difference is this changes, domain doesn't, all real numbers, and the range as a result of this horizontal asymptote that changes to y equals 1 also changes to 1 to infinity. So those are the changes that take place. Consider the function f of x equals 4 to the power of x. Write the function that results from the given transformation, shifted 3 units upward. So just add 1, add 3. So the next one, let's call it g of x, is the same function, 4 to the power of x plus 3. shifted 5 units left. Again, we're going to go to the original one, the way this is given. Okay. Sometimes they want you to use the transformation on the new one, but this is going back to the original one. 5 units left. So x becomes x plus 5. We call it h of x is 4 to the power of x plus 5. Again, going back to the original one, reflected about the x-axis. So when you reflected about the x-axis, you have an effect on the y. And remember, f of x of y becomes negative. So you put a negative in front of 4 to the power of x, and we call it k of x. Again, we go back to original function, and this time about the y-axis. If you reflected about the y-axis, x becomes minus x. We call it I of x is 4 to the power of negative x. The graph below is a transformation of f of x equals 2 to the power of x. Write an equation for the graph shown. So, of course, we know the graph of y equals to the power of x, how it looks like. And what do we notice about this function? Obviously, the y-intercept has a location 0, 2, and this is your horizontal asymptote y equals 3. So these are significant. We notice that. So we start with the basic function. Okay, so those are the two things we notice immediately. So f of x is 2 to the power of x, looking like that, right? So notice there is definitely, and again, of course, it's important to know the location of y-intercept. Now, if you reflect it across the x-axis, that means put a negative in front of it. Okay, reflected across the x-axis. So what happens? Clearly, we get this graph, and this one now 0, -1. So we still have the same horizontal asymptote y equals 0. So if you compare these two, this seems to be the same, has been shifted up, y equals 0, y equals 3, by how many units? 3 units. So when we do that, we see y equals 3, and we see the same y-intercept 0, 2. Therefore, let's give it a name. H of x is minus 2 to the power of x plus 3. So this is pretty straightforward. All right, let's move on. Logs, and we're going to go over something you've seen in previous courses, intermediate algebra, college algebra. So log x base b equals y if b is larger than 0 and b can't be 1. So same restriction that we had for the base of exponential functions. Then y equals log x base b is equivalent to x equals b to the power of y. In other words, if you look at this one, x equals b to the power of y and y equals log x base b, they both have the same exponent y, the same base b. So the exponent is the log, the base is the base of the log. Now, to have an understanding of this, take a look at this arrow. If we can go from logarithmic format to exponential format using the arrow b to the power of y equals x, we should have no problem understanding the properties that come up. So, according to this, the properties, and I'm going to give them numbers so we can go back and forth. Number one, log 1 base b equal to 0. That means if the argument is 1, regardless of the base, it's always 0. Log b base b equals 1. That means if the base and the argument are identical, the answer is 1. Log base b of b to the power of x is x. If you have base b and you raise b to the power of x, of course, you get the x back. And b to the power of log x base b equals x. These two refer to the fact that exponential functions and logarithmic functions are inverse functions. This is a product rule. Log xy equals log x plus log y. All of them have the same base b. This is the quotient rule. Log of x over y is log x minus log y. All of them have the same base b. That's important. Log of x to the power of n is n log x, and they both have the same base b. So product rule, quotient rule, power rule. And by the way, some of them are easily understood if I erase the work. For example, right here, just go with the arrow. B to the power of 0 is 1, b to the power of 1 is b, b to the power of x, b to the power of x. So you can easily see that. Now, there are a couple of specific logs. One of them is called the common log. So log x base, then we don't write it like that. We just write log, and we do not write the base. That means 10 to the power of y equals x. These are the rules. So basically, for numbers 1, 5, 6, and 7, write exactly what you have here. Do not write any base. So that's very straightforward. For number 2, we are saying if the base and the argument is the same, when we don't write the base must be 10. So this is log 10. So that becomes very easy to understand. And this one, same base to the power of x. So the base is 10. So those are easily understood. And I hope everybody is okay with that. So that's common log. Again, by common, we mean the base is 10. Now, ln x means log x, the base is e. When the base is e, we call it ln x, everybody. And here's the rules. And again, first of all, numbers 1, 5, 6, and 7. Instead of log, just use ln. It's very straightforward. But for example, number 2. In number 2, we are saying if the base and the argument are the same. When we write ln, what is the base? E, so the argument must be E as well, and the rest of them follow in the same way. Exponential functions, logarithmic functions are inverse of each other. Therefore, if you graph, for example, y equals e to the power of x and y equals ln x in the same set of axes, then it must be symmetric with respect to the line y equals x. Here's the change of base formula. Log x base b is log x over log b. Choose any base, for example, a. However, we choose either common log, log x over log b, or natural log, ln x over ln b. And if we look at the cross product here, we can get the result here in a moment. But before we go there, I want to show you this. Obviously, is the x-intercept at 1, 0. If we are looking at this portion, that means x is between 0 and 1, then ln x must be negative. If we are looking at this portion where x is larger than 1, then the function goes above the x-axis. and ln x is positive. So that's important to understand, everybody. And now this cross product, let me erase my work, it makes it easier to see. So this cross product, log x base a is the product of these two. Log x base b times log b base a. Notice, if you write it in this fashion, the base remains the base of the first one, and the argument is the last one. So log b base a times log x base b, then you put x as the argument, a as the base. Again, just the cross product here, it's proving that. Now, let's rewrite the equations in one format, from one format to the next. In this case, we are going to rewrite them in an exponential form. So 5 to the power of q is m. Now, of course, we don't see any base, but ln means the base is e to the power of z must be v. Same thing here, we don't see a base. Log, the base is 10 to the power of t is w. Let's go back. Let's rewrite each equation in logarithmic form from one format to the next. It's important to understand 3 to the power of x equals y. That means log y with base 3. Log of the result with this base must be x. What about this one? E to the power of k equals h. Log of h base e must be k. Now log of h base e, that means ln h. Now this one, log of the result b, log b, base is 100, must be a. So log b base 100 equals a. Now state the domain, a vertical asymptote, and the end behavior of this function a, f of x equals log x minus 7. Well, first let's discuss a couple of items here. Logarithmic functions, they have the shape as you can see, and they are inverse function with respect to exponential functions. This one is log x base 10. That means log x, you don't write the base. Log x base e, that means ln x. And this is log x base 2. We have those written because we want to make a point, everybody. So this is ln x. And this is simply log x, okay? Notice, first and foremost, as the base gets larger, remember, e is 2.718 and it continues indefinitely. As the base gets larger, the y-coordinate gets smaller, okay? So it gets closer and closer to the x-axis. That's one thing you want to notice. All of them have the same x-intercept at 1, 0. So when we are dealing with logs, log x base a, where a is positive and it can't be 1, as you can see, the domain is from 0 to infinity and the range is all real numbers. So I hope you see if you compare it to the exponential functions, the domain over there was all real numbers. Now the range is all real numbers. Okay. Also, we have a vertical asymptote, which is the y-axis or x equal to 0. Over there, we had a horizontal asymptote, the x-axis or y equals 0. Now, if if a is larger than 1, it's an increasing function, just like the exponential function. But if a is between 0 and 1, then it's a decreasing function. For example, if we graph this one, which is y of log x with the base 1/3, okay? By the way, the x-intercept remains intact. So if a is between 0 and 1, now this was increasing, this is decreasing. Y equals log x base 1/3. Notice we have the same domain and the range here. We have the same x-intercept 1, 0. So we have the same vertical asymptote. So what you see here, that doesn't change. Okay, and you see 1, 0. So this, first I wanted to give you the general concept. Now going back to this question, we are going to start with log x, which is basically this one. And of course, the x-intercept is located at 1, 0. Now, log of x minus 7. If I replace the x with x minus 7, that means we are shifting it to the right. By how many units? By 7 units. So if initially for this one, the x-intercept was located at 1, 0, now we're going to add 7, and it's located at 8, 0. Let's draw a vertical asymptote. Vertical asymptote, x equals 7. So what happens is that the range doesn't change, it's all real numbers, but this one has been shifted, vertical asymptote x equals 7, then the domain is 7 to infinity. I want to make a point here, and that is, in general, if the question is what is the vertical asymptote right here, you set this equal to 0, okay? You set the argument equal to 0, that gives you the vertical asymptote, okay? And also I want to discuss the end behavior. In other words, what happens when x goes to infinity and negative infinity as far as the y is concerned, okay? So if x goes to infinity, y goes, maybe slow, but it goes to infinity. That means f of x goes to infinity. But if x goes to what? It stops at 7. It can't go further. It has to go to 7. Then it goes down to negative infinity. We write this, and I need to fix this for the sake of the next course. In a moment, I will do that. So first, as x goes to positive infinity, so does f of x. But as x goes to 7, it goes down to negative infinity. The fact of the matter is 7 is not part of the domain as it goes towards 7. But 7 in the sense of limits, when we discuss it in calculus, you're coming towards 7 from the left or right. In this case, we write x approaching 7. This means from the right of 7. For example, 7.1 or 7.0001. If it's from the left, like 6.9999. So this is actually wrong. The proper statement, you may see that in pre-calculus, absolutely unacceptable in the next course calculus. So it's 7 from the right. State the domain, vertical asymptote, the end behavior for this function, g of x is ln of 2 minus x. Well, Let's get started with the basic function y equals ln x. Uh, very basic looking at the x-intercept is located at 1, 0. So far, so. We notice minus x, so we are going to go from y equals ln x to y equals ln of minus x. So if you're changing the x to minus x, what are you doing? Again, assume x is positive and minus x is negative. By the way, that's not a correct assumption. That helps you see that it's reflection across the y-axis. So just reflected across the y-axis, looking like that. So the result is this was the x-intercept at 1, 0. Now the new one, negative 1, 0. Now, how do we go from here to here? We are going to rewrite this in a manner that minus x is incorporated. So minus parentheses x minus 2. I hope you see if I distribute the negative, I get minus x and positive 2. So we have to write it in this fashion because this will help us see that x, this x here, has been changed to x minus 2. So it's been shifted. How many units? 2 units to the right. So from the red one, we go to the green one, and the green one shifts to the right by 2 units. And when it does that, the x-intercept of negative 1, 0 here now moves to the right by 2 units, and it ends up at 1, 0 again, just for the sake of argument. You can draw the vertical asymptote. Clearly x equals 2. And again, before we move on, if they gave you this, you didn't have to graph it, just ask you for vertical asymptote. If they said, okay, what is the vertical asymptote? All you have to do, set the argument of the log equal to 0, and that gives you the vertical asymptote. That's how you find vertical asymptote in general, everybody. So what do we notice as far as the domain and range? I hope you see that the range is not changing, is all real numbers. Domain, everything from negative infinity, and it stops at 2. So domain negative infinity to 2, range negative to positive infinity. Well, so everything is discussed now, the end behavior. I hope you see that when we go this way, x goes to negative infinity, okay, y or the function g of x goes to positive infinity. As we come this way, we stop at 2. So as we go towards 2, g goes down to negative infinity. And again, number 2 is unacceptable. Doesn't go towards 2, but rather 2 from the left, because it's the left of the 2. So proper writing in calculus, x approaching 2 from the left. 2 from the left, like 1.9999. Please understand, it's the concept of a limit, very close to 2. Okay. Same thing, state the domain, vertical asymptote, and behavior. This function is h of x equals minus log of parentheses 3x minus 4 plus 3. And obviously, we're going to start with a very basic function, log x. Y equals log x, which of course looks like that with the x-intercept of 1, 0. So we start with that. That's the starting. When you do the transformation, you start with the basic function. Essential function, you should know the. Now, so we noticed we have log of 3x. So from log x, we're going to go to log 3x. There is a horizontal shrinkage by a factor of 3, which means this shrinks by a factor of 3. And Therefore, if you look at, so it looks like that. And if you look at the first one, has the x-intercept at 1, 0. Now it shrinks by a factor of 3. This one must be located at 1/3, comma 0. So that's log of 3x. Now we are going to rewrite this by taking the 3 out. So log of 3 times x minus 4/3. So this part, we just take the 3 out. I hope you see this is identical to this. But why are we writing to in this format? So we can see what type of a transformation is needed. All right. So what do we need? Well, we are going to change the x to x minus 4/3, then go to the right by 4/3. So shift right by 4/3. So when we shift this to the right by 4/3, then, for example, the x-intercept of 1/3, 0, we're going to add 4/3. We get 4/3 and 1/3, 5/3, 0. Next, we are going to use the negative sign. So the negative sign, if you have a negative in front of a function, in essence, you're reflecting it across the x-axis. So this last one will flip over, looking like that. And so the x-intercept remains unchanged. So we've taken care of everything. What is left is +3. So shift it up by 3 units to get to the final answer. So this thing goes up by 3 units, looking like that. And therefore, the x-intercept that was located at 5/3, comma 0 goes up by 3 to 5/3, comma 3. So what happens as a result? Let's just remind everybody. Here's the graph. Here's the 5/3, 3. Here's the vertical asymptote. What is the vertical asymptote? In short, just if somebody says, okay, what is the vertical asymptote? VA 3x minus 4 equals 0. So x equals 4/3. Okay. So what do we notice now? We notice the domain is from here to infinity, 4/3 to infinity, but the range is not changing. The end behavior, everybody. As x goes to infinity, the y is going down. You see, it's going down to negative infinity. As it approaches 4/3, it goes to positive infinity. Okay, now, as x approaches 4/3, h of x goes to infinity. As x approaches infinity, goes to negative infinity. Now, again, this one, the proper writing is not just approaching 4/3, but 4/3 from the right. Okay, you can come from the right or the left of 4/3. So 4/3 from the right. And this is the final graphing, everybody.